In a universe full of mysteries and unexplored depths, there are forces that can not only change the course of stars, but also rewrite the future of entire galaxies. Sometimes we notice them only through faint clues, altered orbits, abnormal radiation, or unexplained behavior of distant celestial bodies. But when such forces make their presence known, the world of science holds its breath in anticipation. At the intersection of theory and observation, discoveries are made that can change our understanding of the nature of the cosmos. Among many cosmic phenomena, there are special ones that have long eluded telescopes, too rare, too elusive, too powerful to go unnoticed. Their appearance is like a sudden stroke in a picture we thought was complete. Recent data has allowed astronomers to lift the veil on one such mystery. This is not just a discovery. It is a key to understanding the past and predicting the fate of our galaxy. Want to know what exactly happened and why it's important? Then like and subscribe. Things are about to get truly cosmic. Astronomers have made an unexpected discovery. Some of the hypervelocity stars, traveling at speeds of up to 1,000 kilometers per second, have come to the Milky Way from a neighboring dwarf galaxy, the Large Magellanic Cloud. It was previously thought that such stars could only form in the center of our galaxy during interactions with the black hole Sagittarius A, where one star in a binary system is captured and the other is ejected outward. However, new data from the Gaia telescope revealed that about half of the studied hypervelocity stars actually have extragalactic origins. An analysis of the trajectories of these objects and computer simulations led to the hypothesis that the center of the Large Magellanic Cloud contains a supermassive black hole with a mass of about 600,000 solar masses. This discovery is significant because it was previously believed that such black holes existed only in large galaxies, while dwarf galaxies were thought not to contain such objects. This view now requires revision. Moreover, it has become clear that the ejection of stars is influenced not only by the presence of a black hole, but also by the motion of the galaxy itself. This changes the approach to future research on hypervelocity stars and provides a clue to understanding the dense star region in the constellation Leo, which likely formed from stars ejected from the Large Magellanic Cloud. Ongoing work with Gaia telescope data will continue, offering new opportunities to understand processes occurring in galaxies and around supermassive black holes. What will happen to our solar system when the Milky Way collides with the Large Magellanic Cloud? Could the collision of black holes alter the structure or behavior of the entire galaxy? A massive object with a mass of about 600,000 solar masses is likely to collide with the Milky Way in the future. Currently, this object orbits the Milky Way at a distance of approximately 160,000 light-years, and scientists are certain that over time, it will gradually approach us. This rapprochement will occur slowly and will culminate in about 2 billion years. When the two galaxies merge, the black hole at the center of the Large Magellanic Cloud will begin its movement toward the center of the Milky Way. There, it may merge with the already existing supermassive black hole Sagittarius A star, forming an even larger and more powerful object. What new data could reveal previously unexplored aspects of black hole behavior? Why does the black hole Messier 87, visible in minute detail, seem more predictable than the ancient giant Ton 618, whose shadow stretches for entire weeks of light? To truly understand what such a merger might lead to, it's important to consider not only objects within our galaxy or its immediate surroundings, but also more distant and large-scale systems. Observations of other black holes become key elements in constructing a comprehensive picture of their evolution, their impact on the environment, and their role in the structure of the universe. A particularly valuable example in this context is the black hole in the galaxy Messier 87. This elliptical system, one of the most massive in the local supercluster, is notable for its active core, which contains a supermassive black hole. M87 demonstrates how black holes can structure galactic space by ejecting relativistic jets, heating interstellar gas, and regulating star formation. Understanding such processes is critically important when studying more distant objects, such as TON 618, one of the most massive black holes known to date. Its mass exceeds 60 billion solar masses, going beyond the limits of current theoretical models. Although the light from it has been traveling towards us for almost 11 billion years, modern observational data allow us to analyze processes that occurred in the early universe. However, such distant objects are not yet accessible for direct visualization. This is why local examples, like M87, become the foundation for building models that describe the behavior of matter near the event horizon. Through precise measurements of mass, the dynamics of the accretion disk, and the characteristics of the relativistic jet, it becomes possible to extrapolate the knowledge gained to more distant and exotic systems. Each new piece of information about black holes, whether they are located within our galaxy or giants like TON 618, brings us closer to understanding the mechanisms of their growth, interaction, and fate. This knowledge is critically important not only for predicting future collisions, but also for understanding the role of black holes in the evolution of galaxies and the universe as a whole. If you want to keep up with the most exciting discoveries in space, subscribe to the channel and stay with us. There are many more fascinating stories about the mysteries of the universe ahead.